In this video, we're going to talk about transformation of functions. So our goal right now is to find an easy way of visualizing graphs without me having to have technology to plug it into or creating a table of values and graphing it. I want a way of kind of visualizing what's going on. And that's what these transformation of functions is going to do for us. It's going to give us a way for visualizing. So let's start with some basic transformations. And the first type of transformation we're going to look at is a vertical shift, meaning we would vertically shift a function. So what I want you to think of is those toolkit functions, those functions you're supposed to kind of be familiar with. Those might be functions we might do a vertical shift. So here's how a vertical shift looks. So let me select. So given a function f of x, so f of x is a function we know, like one of the toolkit functions. G of x is a brand new function, and it's defined based on f of x. And here's how we're going to define it. F of x plus k. K is a constant. That's stated right below. This is a vertical function where all of the output values have increased by k. So it's our output values. If k is positive, that means the graph shifts up. So if we add values to all the outputs are increasing and it's shifting the graph upwards. If we are looking at k being negative, that's subtracting their values, and therefore the graph is shifting downwards, kind of like you would expect to happen. So let's look at an example of a function based on a table. So this table of values, this is f of x, and we're defining g of x to be f of x minus 3. So the idea is whatever f of x is, whatever value we get for f of x, g of x is going to have the same input, but a output value that is 3 smaller. So here's how that's going to look. And thankfully, this is pretty straightforward. It will get a little bit more complicated, but we'll tackle that when we get there. So all of the inputs stay the same, but all of the outputs are going to be down 3. So they're going to be minus 3. So 1 minus 3 is going to come out to negative 2. That's going to come out to 0. 7 minus 3 is 4, and 11 minus 3 is 8. So those are the values that g of x would take on with those same inputs. This example looks at an equation. This equation maps the height of a ball, and specifically, this is a ball that's thrown on the ground. So somebody throws this ball from the ground, and this is going to predict the height of that ball. But if the ball was instead thrown from the top of a 10-meter building, that is a vertical shift. We are increasing the height up to 10 meters, which means if I want to say what happens to the equation, I would create a new equation based on the building now, which they called b of t, and that's going to be negative 4.9 t squared plus 30 t, and then I'm going to add 10 because 10 is basically behaving like k is in a vertical shift. So I just add 10 to the original function. And it is that simple. There's no like terms to combine. So that's actually the answer. If there was like terms, I would add those together. But there you go. That's how that vertical shift would look. Those aren't too complicated. Horizontal shifts get a little bit more complicated, but we'll kind of step through that. So a horizontal shift defines g of x based on f of x to actually affect the input values this time. And I did notice there was an error here on my notes. Change that to be input instead of output. So we are shifting or increasing the output, the input values by k this time. That's why it's added to the x. It's next to the input. And because of that, it actually kind of works differently than we'd expect. So because we're adding it to the inputs, when we add a value, that ends up shifting the graph to the left. Kind of feels counterintuitive. You feel like if you add a value, it should possibly shift the whole graph to the right if it's to the input, but it isn't. It actually goes to the left. And then if it's a negative, it ends up going to the right. Let's kind of look at why that is. Using the table example. All right. But this time we're defining g of x to be f of x minus 3. Okay, now that changes things a little bit. So this is going to affect the inputs instead. In fact, the outputs of g of x are going to be the same outputs. It is going to be 1, 3, 7, and 11. But the inputs are going to be affected by this minus 3. But it's not in the way you expect. We're not going to subtract 3 from each input. Here's what we have to do. Since g of x is based on f of x minus 3, that's how we've defined it. All right. If I plug in a value for g of x, like let's say I plug in 0, all right, then I'm going to plug that 0 actually into f of x, but I'm going to do 0 minus 3 first. So really what I'm going to need is f of negative 3. That's actually information I don't have. This table doesn't tell me when f is negative 3. So rather than plug in 0, I'm going to plug in a value so that I get out a number I do have on this table. Like I'd like to get out 2 is what I'd like to get out. So in order to get out 2, if I know I'm going to subtract 3, I need a 5. So g of 5 is going to be f of 2. It's going to be the same value as f of 2, which happens to be 1. So my input value is going to be 5, because when I plug in 5, I get out 1, just like f of x. Let's do that again for the next value. Let's say this time I would like it to be f of 4, which is a value I have on the table. So I would need to plug in, or I should say, in order to get out 4 when I subtract 3, I would need a 7, because 7 minus 3, I got that wrong, is going to equal 4. Which means g of 7 is going to equal the same thing as f of 4, which is 3. Okay, now I want to pause and I want to come back to the table, and here's what I want to notice. The x values from here to here, so from 2 to 5, that's a difference of 3. In other words, I added 3. Same with the 4. I added 3. So if I'm going to use that pattern, 6 is going to be 9. 9 is going to produce for me f of 6, the same value f of 6 gets, the same output value that f of 6 gets. And for the last one here, then, if I use the pattern of adding 3, that's going to be an 11. So it's kind of doing the opposite of what we would expect, which is what I was saying. Because in order to subtract a 3, it ends up actually adding 3 to the input values. And that's why the direction that a horizontal shift goes kind of goes the opposite of what we expect. When k is positive, it shifts left. When k is negative, like in our example, it shifts right, because we're adding, not really subtracting, in order to make these values work. A little bit interesting that way. Kind of goes the opposite of what we expect. Okay, so this particular graph is using the original x squared toolkit function. Now, the original x squared goes through 0, 0, and then it goes through 1, 1, negative 1, 1, and then it goes through 2, 4, and then I'm not going to draw the other part of this because I don't need to. I can see from here, it looks like all of my values have shifted over 2. So basically then, my new function g of x is shifting to the right 2. So in order to make that work for f of x, I have to do the opposite. I'm going to subtract 2 from x, which visually what that looks like in the equation is x minus 2 squared. So that is g of x. It's x minus 2 squared. That is a right shift on the parabola of x squared. That's how that equation is going to play out. All right, let's try another one. Let's see. This time we're given the square root function, and the transformation is f of x parentheses plus 2. So is this a vertical or horizontal change? Well, this is going to be a horizontal change since we added it to the x. It's added to the input. Is it going to shift left or right? Well, because we are adding a positive number, it goes the opposite way. We'd think it's going to shift left 2 units. Now they ask us to graph this, both graphs, in fact, on the same axis. So I'm going to just do a rough sketch here of these. All right, so that's -3, that's 5. And then 2, 3, 4. And then that's -1. Okay, great. So there we go. So the square root function goes through 0, 0, 1, 1, and then 4, 2. I've memorized that since it's one of the toolkit functions. You can go back and look at those if you need to, but that's what the square root function looks like, the original. Now, that'll be my f of x. G of x, however, is going to be shifted 2 units to the left. So instead of starting at 0, 0, it's going to start here at -2, 0. And then it's going to follow the exact same pattern. So it's going to go there, and then I would count 1, 2, 3, 4, and there you go. So I've shifted all of my points to the left too. And there you go. So that is how we graph. Because I have toolkit functions memorized, basically, I know them, it makes it easy to do this kind of graphing. All right. This time we're looking at a more exciting example because there's more than one thing going on here. Okay. So we're using the absolute value function. All right, and they're asking us to sketch this. So here's what that ends up doing to our absolute value function. So +1 is going to end up shifting this thing left 1, goes the opposite way. That's the left, right. The -3, that's a vertical shift. I expect this is going to move it down 3. So the original function, square root function, I'll do here in red, just goes through the diagonals. It's a V shape going through the diagonals. So the function, when I shift it left 1 and down 3, that means the base of the V is going to start right here at -1, -3. And then I'm just going to basically replicate the graph I did, kind of go on the diagonals. I kind of just imagine as if that's the new origin and kind of graph it the exact same way. And there it is. There's the sketched graph. By the way, if I write this function as an equation, it would just be absolute value x + 1 - 3. Basically plugging in the x + 1 in for x in the original f of x function here. So plugging it into here, and then I'm minusing 3 from the outside. So that's how the new equation looks. Okay, so let's try another one. This time we're given a graph and we're asked to write a formula for it. So for this, that looks like the square root function. We graphed that earlier. Okay, cool. So normally the square root function starts here at 0, 0. So this looks like it has been shifted right 1 and then up 2. Okay, so that means then for the square root function, I'll just do an f of x. So square root. So if I'm going to do a right 1, that means I'm going to -1 from the x. But then the vertical shift of up 2 is just going to be a +2 outside of the square root. And that would be the equation. That is a right shift and then up 2.